I learned from one of your classmates that your unit test was on Thursday, and given that Mr. Ruby hasn't taught you much since he had his baby, congratulations, Mr. Ruby, by the way, I thought I might take up some review work. So, first, let's go ahead and talk about moles and molar mass. And I do have the College Board website on my phone, just so that I can have a little bit of agenda. So, molar mass is just, if you look on the periodic table here, the little number on the top right-hand corner, that is the molar mass. So, for example, hydrogen, it's 1.008 grams per mole. Helium, 4.006, and so on and so forth. Now, this mole here represents Avogadro's number of things. It's literally just a measure of counting, which is 6.022 times 10 to the 23rd. 1/mole. This is how many things are in a mole. This is Avogadro's number. It's going to be very important. And so you might have seen a graph where you have relative abundance on the y-axis, abbreviated RA here, and then the mass number on the x-axis. And you might have also seen some sort of straight lines protruding out. This is a mass spectra of elements. So, for example, if we were to use, say, iron, so we'll say that this is 55, this is 56, and 57. And obviously, I'm not going to scale. This is kind of like an eyeball. But if you have each of these relative abundances, you can take a weighted average and you can find the molar mass of the element. And so you have pure elements and you have substances. This is onto unit 1.3. And I am going pretty quickly. You can slow down whenever you need to. So, elemental composition of pure substances. We can say ammonia, down here, by the way. So, ammonia, NH3, has 1 nitrogen and 3 hydrogens. That's what the formula tells you. Sorry, 3 hydrogens. That is what the formula tells you, and that is the elemental composition of that pure substance. Now, if that pure substance was impure, it was mixed with something, you could also have some water in there. You could also probably have some, chlorine in there or something, right? So, this is where you get into mixtures and composition of mixtures. You might have seen a problem given that an impure sample of iron, say, back up here, is with iron 3 oxide, which is rust, and some other chemicals. You might have seen a problem where you have the mass of the total and the mass of pure iron in the total. So you might want to find the mass percent of iron in that mixture. You just take the mass of iron over the mass of total, that's your percentage. Well, multiply by 100%, but that's your percentage. You might also want to use some other techniques to do so, like some stoichiometry, some other stuff. You can probably get into that in later units. So, moving on to electron configurations. I'm just going to go ahead and give myself some space down here below the periodic table. So, up here, this is, you might have actually labeled it, this is called the S block. So this entire thing, from hydrogen down to francium, groups 1A and 2A are the S block. This is the P block, from boron down to nihonium, over to organoson. This is called the P block, and you basically have to use p orbitals to define this, except for helium, of course, which is part of the S block. It's kind of confusing, as one S only wants to do it. So, for electron configurations, you just go in order. So say we want to find fluorine, right? We can have fluorine be the combination of 1s2, 2 1s electrons, 2 2s electrons, and 5 2p electrons. Now, you can also abbreviate this as a shorthand, which is to use the nearest noble gas. Not the nearest past. So you can abbreviate this with helium, which is 1s2, and then go 2s2, 2p5. This is still fluorine. So this is fluorine, and this is also fluorine, because these are the same thing. So moving on to photoelectron spectroscopy. I know I am going kind of fast. You can always zoom back or slow down whenever you need to. Photoelectron spectroscopy, you might have a graph that looks, you might have a graph that looks kind of like this. I'm not exactly going straight, but oh well. On the x-axis here is binding energy, abbreviated BE, and on the y-axis here is relative abundance. Relative abundance. I'll just label that A. And so you might have seen a graph that looks kind of like this, where you have sporadic peaks all throughout. This is 3 times, and this actually represents your electron configurations yet again. So what photoelectron spectroscopy basically is, it's measuring the binding energy of different electrons. And so the theory behind that is, as you go closer and closer to the nucleus, as you go more and more into core electrons, you begin to have more and more binding energy to that nucleus. It's sort of further to the left on this x-axis. So the furthest is always going to be a 1s2 or a 1s1, depending on what sample you're dealing with. And then you can basically just do this kind of like your normal electron configuration. And right now you can see that I have done neon. So this would have been photoelectron spectroscopy of neon. And now for periodic trends, which honestly is kind of the linchpin of Unit 1. And so it's basically telling us how everything goes from the periodic table. You might have heard the terms electronegativity, denoted En here, electron configuration, electron affinity, denoted EEA here, ionization energy, denoted IE here, and some others. Can't remember them all off the top of my head, but I need to go pretty fast here. So IE is ionization energy. Now you may recall that as you go to the left or to the right of your period, your ionization energy goes up. This doesn't come as a surprise. As you go to the right of the period, you begin to add more and more electrons, and that that atom really wants an octet. And so it will do anything it can to achieve the octet, especially over here in the nitrogen, oxygen, fluorine, chlorine group, right? The purple group here is called the halogens. They have very high ionization energies, and they really want an octet. So most likely you're going to see them as a negative ion, which they have gained an electron. This is called electron affinity. So generally, atoms that are more down and to the left of the periodic table will have less ionization energy, so lower IE, and groups that are higher and to the right have a higher IE, or ionization energy. So this is kind of like electronegativity. Now, electronegativity essentially just means how much can this atom pull electrons towards itself. Again, this is the general trend. You might have some weird specific ones that have differing from the trends, but this is the general trend. For ionization energy, it was more down and to the left is lower, more up and to the right is higher. It's the same for electronegativity. So more down and to the left is more of your like 0.4 is 0.7 value, right? And up here towards helium, fluorine is the highest with 4. This is more of your like 3.5, 4 values, right? And so these two can actually form ionic compounds when their electronegativity difference is a bit higher than a certain value. And then electron affinity, it's kind of always negative. So electron affinity is down here and down and to the left. You might have already noticed a pattern, but down and to the left, electron affinities are a little bit less negative than those up and to the right. There are some weird exceptions, so you might want to document those before you go into your unit test. But otherwise, those are the general trends for electronegativity, electron affinity, and ionization energies. And finally, let's go ahead and end off this unit review video with valence electrons and ionic compounds. So this section is all about electronegativity. What electronegativity does is basically it determines how like the atoms will bond. So if you have an electronegativity difference, which I will denote with a capital Greek letter delta, I could go into the schematics of how that's done, but not enough times here, sorry. We'll say delta En. If it's less than 0.5, generally that is considered a nonpolar molecule. Nonpolar. If it is greater than 0.5 but less than, I believe, 2.5, see, greater than 0.5, sorry, greater than 0.5, less than 2.5. Again, I can't think of it off the top of my head. You may want to fact check me on that, but generally this is considered a polar molecule, unless there's some sort of weird symmetry stuff going on. And of course, anything greater is generally considered ionic. So if you have greater than 2.5, this is considered ionic. And of course, you should already know how to name ionic compounds, but if you don't, the anion, which is negative, it has an "ide" suffix generally. There are some polyatomic ions where you can get into ites, eights, or others, but generally it's going to be ides. And the cation is just going to be the element name. So you can have sodium chloride. That's sodium as the cation, chlorine as the anion with that ite suffix. I do hope that this video will help you get 100 on your test, and I will see you next unit. Bye.